What we're going to be looking at now in this video is the derivatives of vector valued functions. What you're going to notice, and we're going to talk a bit about this, is a lot of the stuff that we're going to be doing with vectors and their derivatives, or excuse me, vector valued functions and the derivatives, is going to look an awful lot like what we would do with regular functions or normal functions. We're just going to add in some wrinkles, and some of those wrinkles are going to be things like we've got a dot product of vector valued functions, we've got a cross product of vector valued functions. What happens when we take the derivative of the dot product? We take the derivative of the cross product, and we're going to actually see some properties that will allow us to simplify that process. Okay, and in addition to that, we're going to be talking a little bit about how do we find tangent lines and how do we utilize tangent lines in order to find special information about space curves, for example. So hold on tight. When we are taking the derivatives, it's not going to be all that bad. You're just going to have to kind of go back into the not too long ago, I hope, archives. Remember, how do you take derivatives of certain functions? And that should actually make it a lot easier for you to find the derivatives of vector valued functions. All right, so now what we're going to start out with is we're going to look at the derivative of a vector valued function. What I love sometimes about math textbooks, and this is from Herman and Strang, our Calculus 3 book, is that basically we've got to set up, if you're going to write a textbook, you've got to set up, this is the definition of a derivative, and then we're really not going to use it. I mean, you used it back at the beginning of your Calculus 1 class, but for our purposes, we're not really going to use this thing here. But what is going to be valuable is that we're going to see this and we're going to see, oh, you know what? Yep, that's a derivative, right? This should look exactly like what you see when, or what you think about when you think about the definition of a derivative. The difference here is that we're going to be, we've got our vector function, r, and then the derivative of a vector valued function is going to be a derivative as well, is going to be a vector valued function as well. So that's actually a key point, that when we take the derivative of the vector valued function, we get another vector valued function as a result. Otherwise, we talked about limits. The limits work exactly the same way, except you're going to take the limits on components. So here's probably our more practical way of thinking about differentiation, or taking the derivative. Essentially, we've got either a two-dimensional function, this is number one, right? Two-dimensional vector valued function, it's got an I and a j, or we've got a three-dimensional vector valued function, an I, j, and a k. And if you take the derivative of the vector valued function r, what you want to notice is that we've got f of t, g of t, and h of t. Those are the functions that we have for I, j, and k. And then the derivative is just the derivative of each one of those functions for I, j, and k. So essentially, what we're going to be doing is we'll take the derivative of the components and make them the new components of the new vector. And that's it. So there we are. And we'll do that, and I'll show you exactly what that looks like. It's not too brutally hard. I hope. So let's find some derivatives. We'll start out with this. We've got r of t is equal to 6t plus 8i plus 4t squared plus 2t minus 3j. So we'll look here. I'm going to have f of t is just going to be 6t plus 8. It's going to be the part of the ith component. And then we'll let g of t equal 4t squared plus 2t minus 3. F prime of t, the derivative of 6t plus 8 is 6. And g prime of t is equal to 8t plus 2. So consequently, r prime of t, my vector valued function derivative, is going to equal 6i plus 8t plus 2j. And there's the derivative. That's it. Right? Great. Let's do another one just in case you didn't catch that. What we're going to do, we've got r of t here is equal to e to the t sine ti plus e to the t cosine tj minus e to the 2tk. So what we've got here, we've got a couple product rules, but that's fine, right? What I'm going to do is, I'm going to kind of do it all at once. R of t is going to equal, and then I'll take the derivative of e to the t sine t. So that's going to be e to the t sine t plus e to the t cosine t I plus, and then we'll have e to the t cosine t plus, or minus rather, minus e to the t sine t using our product rule, j, and then we'll do minus 2e to the 2t k. because the derivative of negative e to the 2t is negative 2e to the 2t. And that's it. There's the derivative of your vector valued function. So that's it. All you're going to be doing is you're going to be taking the derivative of each component, okay, and then slapping them back together in the order in which you took the derivative. And that's your new derivative. Something to notice, that the derivative derivative of a vector valued function is a vector valued function. And another thing to notice too is that it's going to maintain its dimension. So notice that the derivative of the two-dimensional one is a two-dimensional, and the derivative of the three-dimensional vector valued function is a three-dimensional vector valued function. Okay, now let's take a look at the properties of the derivative for vector valued functions. So you're not really going to memorize these, but you do really want to know them. I think probably eventually, if you did enough work with them, you would eventually memorize them. I'm going to be using them in proofs later on inside of the course. And so I want you to kind of look at them, make sure that you understand what it is that I'm talking about when I do, say for example, take the derivative of a dot product. Okay, so for example, big ones here that might be look a little strange: the derivative of a dot product, the derivative of the cross product. Okay, some things to note: they look an awful lot like, say for example, the chain rule. Right? If you look at them, they kind of look like chain rule, or actually not chain rule, but more like the product rule, and they're just a special kind of product. Okay, and then also this the scalar product here, which actually is also basically your product rule, except utilizing the derivatives of vector valued functions. Okay, so as we're working with these properties of the derivative for vector valued functions, just remember that they're kind of there. I'm going to bringing them up. It's like, okay, there's that. That's what happens when I take the derivative of the dot product. It kind of does something a little bit different. That's a bit more like the product rule. This chain rule right here, I want to actually point out something about it too. This is a function f of t. This is not a derivative. All right, it does say that f is a differentiable real valued function, but I just want to not a vector valued function. So f is not a vector valued function in this case, and that's actually an important piece right there. Okay. Because I now that I think about it, I'm not even sure what it would look like. And then this might actually come in really handy later on as we do more proof work, that I've got r of t dotted with r of t is equal to some constant, then r of t dotted with r prime of t is going to end up equaling 0. Okay? And that actually is going to be kind of handy too. All right? So go ahead, you're going to study them a little bit. We'll use some in just a moment. So you can see how it is that something like this can sometimes make taking a derivative easier. So let's say, for example, that what we want to do here, we're going to have r of t is going to be this one, 6t plus 8i plus 4t squared plus 2t minus 3j plus 5tk. And then u of t is going to equal t squared minus 3i plus 2t plus 4j plus t cubed minus 3tk. So we've got two vector valued functions, and what we're going to do is we're going to find the derivative, d dt of, and we'll start out with r of t dotted with u of t. And also we're going to find d dt of r of t crossed with u of t. Now, what we'll do first, right, we've got the derivative here, d dt of r of t dotted with u of t is going to end up equaling r prime of t dotted with u of t plus u prime plus r of t dotted with u of t, u prime of t, excuse me. All right, and notice the order, because this order matters. So r prime of t dotted with u of t plus r of t dotted with u prime of t. So we'll first find r prime of t. R prime of t is then going to equal, we'll start out with the first component, 6i plus 8t plus 2j plus, and then 5tk, so plus 5k. All right, so 6, 8t plus 2, 5. Then u prime of t, which is going to be the other derivative that we need, u prime of t, is going to end up being 2ti plus 2j plus, and then 3t minus 3k. 3t squared minus 3k. Excuse me. Or 2t, 3t squared minus 3. Now I'm going to plug that into my function. So I'm going to first find I've got r prime of t dotted with u of t. So that's going to be, we'll just take this, it's going to be 6, 8t plus 2, comma 5, dotted with t squared minus 3, 2t plus 4, comma t cubed minus 3t. So that ends up equaling 6t squared minus 18, because we'll take 6 times t squared minus 3, plus 8t plus 2 times 2t plus 4, plus 5 times t cubed minus 3t. So this gives me 6t squared minus 18 plus 16t squared plus, and then this would be 4t plus 32t, so plus 36t, plus 8 plus 5t cubed minus 15t. Combine my like terms, and what I get here is I get 5t cubed plus 22t squared plus 22t squared plus 21t minus 10. And that is going to be r prime of t dotted with u of t. Now we need to do r of t dotted with u prime of t. So we'll take our dot products again. That's going to be then 6t plus 8, 4t squared plus 2t plus minus 3, and 5t. And we'll dot that with our u prime of t, which is going to be 2t, 2, and 3t squared minus 3. This will then equal 12t squared plus 16t plus 8t squared plus 4t minus 6. So I just took 2 times this function. Plus 5t times 3t squared minus 3. So that's 15t cubed minus 15t. Combine my like terms. I get 15t cubed, 12, 20, so plus 20t squared. Then 16t minus 15t is 1t plus 4t, that's 5t, plus 5t, and then minus 6. And there's the second half of my equation. So now I've got to add the two together. I've got to add r prime of t dotted with u of t and plus r of t dotted with u prime of t. So that means that I'm going to take this function here, or this equation, 5t cubed plus 22t squared plus 21t minus 10 plus 15t cubed plus 20t squared plus 5t minus 6. Combine my like terms. There's 5t cubed, that's 20t cubed, plus 42t squared, plus 26t minus 16. And that is equal to d dt of r of t dotted with u of t. Bit of a process. You can go back and do it the other way around though. You could take the dot product of these other two functions. Now, one thing you might notice that actually kind of is handy is that when we took the derivative, we kind of reduced each one of these values by a power. That made things a bit easier for us, okay, in terms of the multiplication, when we actually had to go through and do the multiplication. So notice all I had to do was I just kind of traded in this, the derivative in for its equivalent equation, which is basically what we call the derivative of the dot product. Let's try now to do the derivative of the ddt of r of t crossed with u of t. Remember, r is going to end up equaling, we'll write it as a vector, 6t plus 8, comma 4t squared plus 2t minus 3, comma 5t. It's r prime ended up being equal to 6, 8t plus 2, and 5. Then we have u. U was equal to t squared minus 3, comma 2t plus 4, comma t cubed minus 3t, and that's going to then be equal to 2t, comma 2, comma 6t squared minus 3. And there's that's u prime. The derivative of the cross product is thus going to equal r prime of t crossed with u of t plus r of t crossed with u prime of t. So we'll start out, let's find out this first piece right here. I've got I, j, and k. I, j, k. This gives me 6t plus 8, or excuse me, not 6t plus 8, but 6, 8t plus 2, 5. The cross product is going to end up giving me, I've got 8t plus 2 times t cubed minus 3t minus 2t plus 4 times 5. I minus 6 times t cubed minus 3t minus 5 times t squared minus 3 j plus 6 times 2t plus 4 minus t squared minus 3 times 8t plus 2. So that would end up being the cross product for r prime of t cross u of t. And then we have r of t crossed with u prime of t. And that would end up being I, j, and k. Okay. And we'd have r of t is 6t plus 8, 4t squared plus 2t minus 3. And then our k is going to end up being 5t. And we will cross that with 2t, 2, and 6t squared minus 3. So that would then end up being equal to the quantity 4t squared plus 2t minus 3 times 6t squared minus 3. I minus 6t plus 8 times 6t squared minus 3 minus 2t times 5t j plus 6t plus 8 times 2 minus 2t times 4t squared plus 2t minus 3k. Whew, that's a lot. Once we go out, we actually have got to go in and we'll go in here and we will in fact find the cross products. And what we'll get is we'll end up getting two vectors, right? Two three-dimensional vectors, and they'll get added together. And their sum will actually end up being the derivative, right? So that one actually takes a little bit of time. I'm going to let you actually do that one on your own, finish that one up on your own, or don't, and just make sure that you have the idea, okay? All right, so this is actually how we utilize some of those properties of derivatives. It can sometimes be really lengthy because, you know, taking cross products and dot products of vector valued functions can sometimes take a little while, okay? It's a little bit more time consuming, not more complicated, but more time consuming than doing it with just constant valued functions. So the next important idea that we need to address is the notion of the tangent vector or the unit tangent vector. All right, so you should really be thinking, when I say tangent vector or tangent line or anything else like that, it should always be derivative, right? Because the slope of the tangent line is one way to conceptualize the derivative. And so consequently, when we talk about a tangent vector, you should be thinking, well, it's got to have something to do with the derivative, okay? In fact, when we talk about a tangent vector, it is a vector that is in the direction of the curve at the particular point, okay? And so, like, basically, it kind of helps us to define what the direction of the curve is, right? Just like a derivative defines what the slope is of a curve in two-dimensional space. The tangent vector is going to tell us what the direction of the curve is in three-dimensional space, right? It's going to say, oh, it's pointing over there. When I'm at this point right here, it's going to point in this direction over there, okay? And that's going to be the notion that we're going to get from the tangent vector, okay? I'm going to actually post another video up here where I talk about like finding the angle between two vectors, and what's given inside of that video is actually a pretty good representation of what it looks like to have a tangent vector to something in space. So we imagine that we have this curve, like I've got a curve in space, right? And like you kind of imagine the curve kind of moves, right, in a lot of different ways. And so what I'm gonna say is I'm gonna say, okay, well, I want to imagine what my tangent vector is. So if the curve is moving in this direction, my tangent vector, right, is going to move in the direction of the curve, okay, but it's going to be linear. So it's a line or it's a vector in the direction of the curve at that particular point. And that's going to define for us what a tangent vector is, okay? And that's actually going to be the important piece that we're going to get here about tangent vectors. We'll find them, no problem. The big idea here is that a tangent vector and then a unit tangent vector, which we'll talk about in a second, are going to be in the direction of the curve at whatever point we're looking at. All right, so here's our definition that we're going to be utilizing here. Let C be a curve defined by the vector valued function r, and then we're going to assume that r prime of t exists when t equals t naught. So a tangent vector v at t equals t naught is any vector such that the tail of the vector is placed on the point r of t naught on the graph, and the vector of v is tangent to the curve c. Tangent, I want you to be thinking to yourself, okay, that's in the direction of the curve c at that particular point. It's just kind of like, it's going that way, right? That's the idea. It's going in a particular direction. The vector r prime of t naught is an example of a tangent vector at the point t equals t naught. So we'll pick a particular value for a parameter, right? A lot like how we were doing parametric equations before. We're going to pick a particular value for that parameter, okay? And if we assume that r prime of t is not the zero vector, right? By the way, that's the zero vector, not 0. Then we can also have something called a principal unit tangent vector at t, okay? Which is basically, it's a unit vector. So remember, it's a vector of length 1, and now it's going to be in the direction of the curve at that particular point, in this case t, or at t naught. So that's our definition. All this is meaning is it's basically saying, okay, look, my tangent vector is going to be the derivative of the vector valued function. I'll figure it out at a particular point t, right? T equals whatever t naught is, a particular value that I have for t, okay? And if I want to find a unit tangent vector, okay, or the principal unit tangent vector, I'm going to have that derivative, and then I'm going to divide it through by the magnitude of the derivative, which is exactly what we have been doing thus far in order to find unit vectors. So let's take a look at an example. Let's say, for example, we have this. R of t equals cosine ti plus sine tj. This should be, you should be saying to yourself, oh, that's a circle. So circle of radius 1. And we were like, okay, well, what does it look like? What's that unit tangent vector going to look like here for this particular object? So I'm going to find r prime of t, okay, because the first thing that I'm going to need for this big T, my unit tangent vector, is r prime of t. And so the derivative of cosine t is negative sine t I plus then cosine t j. And that's r prime of t. Then I go find the magnitude. So the magnitude of r prime of t is then going to equal the square root of negative sine t squared plus cosine t squared, which is just equal to the square root of sine squared t plus cosine squared t, which is equal to root 1, which equals 1. So my unit tangent vector to this curve is going to end up being equal to negative sine t I plus cosine t j divided by 1, which is just negative sine t I plus cosine t j. Okay, which, by the way, is still a circle. It's just in a different orientation, right? We've got our unit tangent vectors for this particular object are going to be the same as the actual function. They're just going to have a different orientation. Okay. All right. Let's try another one. Let's suppose that we have u of t. Okay, and that's going to equal 3t squared plus 2t I plus 2 minus 4t cubed j plus 6t plus 5k. I'll first find u prime of t. So u prime of t is going to end up being 6t plus 2 I plus negative 12t squared j plus 6k. So there's my vector. Okay? And then I'll find the magnitude of u prime of t. And that's going to then equal, okay, it's going to be the square root of 6t plus 2 squared plus negative 12t squared plus 6 squared, which equals 36t squared plus 24t plus 4 plus 144t to the fourth plus 36, which is going to end up equaling the square root of 144t to the fourth plus 36t squared plus 24t plus 40. And what we could do there is we could actually pull out a 4. So this is going to be 2 times the square root of 72t to the fourth plus 9t squared plus 6t plus 10. And so our unit tangent vector, t of t, is going to end up equaling 6t plus 2 I plus, or minus, minus 12t squared j plus 6k divided by 2 times the square root of 72t to the fourth plus 9t squared plus 6t plus 10. All right, I know it's quite a lot of work when we're talking about vector valued functions. When you actually start working with these more, when we start seeing them inside of other places, when we start talking about curvature and arc lengths and things like that, we've got to utilize these unit tangent vectors. You're going to find that you really just have to be very, very careful. Just be very careful when you're finding them, when you're writing them out, when you're simplifying them, because they can get really messy very, very quickly. Okay? So, we've got a unit tangent vector. If you ask yourself, well, what do I need to do now that I've got a unit tangent vector? I mean, like, do I have everything? Well, there's one more thing, right? And that is actually finding the equation for the line that is tangent to the curve at a particular point t. Right? And we're going to utilize these tangent vectors to do that. All right, so let's say, for example, we want to find the equation of the line tangent to the curve, r of t equals e to the t, e to the negative t 0, at t equals 0. So if you remember, in order to figure out the equation of the tangent line, what do we need? Right? Okay, we need a direction, which is our slope. All right, and how do we find that? That's the derivative. And we need a point. Or the point, in this case. The parameterization, we've got t equals 0. So I'm going to find my point first. So the point that I'm going to need here is going to be e to the 0, e to the negative 0, 0, which is just the point 1, 1, 0. So it's 1, 1, 0. Okay? And so basically all you got to do in order to find that point is plug in your t, your value of t, into the equation for the vector, and you're going to get the point, right? Okay? Or, yeah, get the point. There's your point, right? Maybe we can actually use this. There we go. Okay? Now what I need is the direction. It's actually a lot easier than the tangent line because we're actually just going to plug in values for t when we get done. So r prime of t is going to then equal, derivative of e to the t is e to the t, the derivative of e to the negative t is negative e to the negative t, and the derivative of 0 is 0. So I'm going to plug in 0, r prime of 0 then, because we're looking at t equals 0, is going to equal then 1, negative 1, 0. And that's the direction. So the equation of the line that's tangent to the curve, okay, is going to end up being r, we'll write it as a vector, we'll call it u of t, or no, let's call it t of t, tangent of the line, t of t, but little t, so we don't get it confused. T of t is going to equal then, here's our direction vector 1, negative 1, 0, t plus, and then our point 1, 1, 0. And there is the equation of the tangent line. So it's got a great parallel. The parallel is exactly like the parallel that we did in Calc 1. Okay? How are you going to go about doing this? First, you'll plug in the value for t in order to find the point on the curve that you're going to find the line tangent to. So that gives you a point on the line. And then secondly, we'll take the derivative and then plug in t, just like when we did parametrization, or when you did parametrization inside of your Calc 2 class. And that's all there is to it. So when we're working with vector valued functions, taking the derivative of vector valued functions is pretty straightforward. You're going to take the derivative of each component function in the vector valued function, okay, and then you're going to associate them with each component in the derivative, right? That's basically it. We have some properties of derivatives, and you want to make sure that you're acquainted with the properties of those derivatives. You want to remember that, like, when you're taking the dot product or the cross product of vector valued functions, it can get a little messy, okay? Just be careful. Just be careful as you're working. Same thing when you're finding, say, for example, the tangent vectors, and you're trying to find the equation for the tangent vectors, the function for the tangent vectors. That's also can get a little bit messy. And then finally, how do we find the equation of a line, right? The equation of a line, you're going to take the derivative to give you the direction, which is our slope, okay? And then you'll plug in the value for t in order to find your point on the line. Put those two together, you end up with a tangent line. So that completes our lesson on derivatives for vector valued functions.